So I thought we're switching gears. We're switching gears a lot. We are switching gears, in fact, so much that maybe it's not even the same vehicle anymore. And I was thinking, Ed, you can stay here if you want. No? You want to stay? No? No, you can stay if you want. No, okay. I didn't want to kick you out. So I was saying, yeah, we're switching gears a lot. You know, we are going to talk about turbulence now. Everything up to now was laminar. Now we're going to talk about turbulence. Everything we talked about up to now was reactive. In fact, now we are talking about non-reactive flow, incompressible flow, and so on. The next lecture here is on turbulence. I just want to give, we're going to talk about turbulent combustion, but before we do this, I want to give you an overview of what turbulence is. So we'll talk about a few characteristics of turbulence, statistical description, this here the so-called Reynolds decomposition. Then we talk about the mean flow equations, something like kinetic energy equation, and then here really this is the core of all of the turbulence theory, is the so-called Kolmogorov theory, and then we talk a little bit about turbulence modeling, and here maybe large eddy simulation. So what is turbulence? Turbulence, I mean, is you could say is composed of eddies that mix, and turbulent flows are random. They are not predictable, not deterministic. They lead to very, very much faster mixing than laminar flows. That's why almost all technically relevant flows for us, combustion where we need mixing, they are turbulent because then you can accomplish reactions much faster. Now, what's interesting is if I take a mixing layer, I have just fuel here, I have just air here, and then I let them mix in a laminar way. It just takes forever. It takes a long time. It's just diffusion. Now, there's one way of mixing, okay? There's another way of mixing where I would say take two immiscible fluids. They wouldn't diffuse into each other. Like here, oil and vinegar, whatever. I mean, or oil and water. And they don't mix with each other really well. And so let's start to stir them. Then in the beginning, I had just, here's fuel, here's oxidizer, and then I start stirring. That's what the turbulence does. Then I get regions that are, just fuel, and other regions that are just air, okay? The turbulence itself, just moves stuff from here to there. That's what it does, nothing else. And so did I increase the mixing rate up to that point? No, because I still have only fuel and air. No mixing has happened. But what I did is I increased the surface area a lot, and because that's not written here, but because turbulence also, causes local strain, I also increased the local gradients. And that, of course, makes mixing much, much faster. So when we think of turbulent mixing, we often we think of it like this. We have here this stirring, and then the stirring leads to surface area, and then we get molecular mixing. Now, when turbulence people, fluid mechanics people think about turbulence, they very often don't care about exactly what the mixing rate is. They worry more about I mean, here I had just fuel, just air, and here they seem to be mixed. Okay, that's what. But for us, it's very important that if you want to have chemical reactions, you need to mix fuel and air really on the molecular level. If the fuel molecule and the oxygen molecule, they're not next to each other, they can't bump into each other, reactions are not going to happen, okay? So for us, it's not the large-scale stirring that is very important. For us, really, the ultimate outcome of how much fuel and air really mix on the molecular level, that's for us important, okay? So that is something we need to keep in mind. Now, the turbulence, we often think of it as these eddies. So here you see we have large eddies, we have smaller eddies, and we have yet smaller eddies. And the other thing you see is if you have a large eddy, then, no, you don't see this here. I should redraw the picture. But if you have a large eddy, if maybe it steers things this way, then inside that large eddy, you can have a smaller eddy. Yeah, it might go the other way. And inside that, you have yet smaller eddies, and they go yet the other way. And that makes up then the, this chaotic nature of turbulent mixing. Now, turbulent eddies is something, maybe the turbulence doesn't really consist of eddies, but we say turbulence has different length scales, and so I associate a length scale with an eddy of that size, okay? It just helps thinking about it. And we have different velocity scales, the large turbulent motions, they might not go like this, but the large turbulent motions, they have a certain velocity associated with them, and the very tiny turbulent motions, they also have a different velocity maybe associated with them. So for me, I think of this as a, spinning velocity of this eddy, okay? So we look then at an eddy like this. An eddy is characterized by a length and by a velocity, okay? And from these two, of course, you get a time scale also. But the time scale is not independent, right? The time is just the length scale divided by the velocity scale. That's not independent, okay? And also we need to keep in mind, we have different size eddies. They can superpose onto each other. And we need to keep in mind that each one of these is characterized, each size is characterized also by a different, velocity or time scale, whatever you want, okay? So, let's see, here's Osborne Reynolds in Manchester in the years, not here, I can't remember, but he was doing his famous experiment. He has this pipe, and he has a flow through the pipe, and then he puts a die in the beginning. Here, there's this black line, the die in the beginning, and then he observes what happens to the die, and nothing happens to the die. The die doesn't really mix with all the rest. And then he increases, he thought, what if I increase the Reynolds number? No, he did not, of course. He thought, what if I increase the velocity? So he increased the velocity, and all of a sudden he sees, all of a sudden, this thing bursts up and mixes instantaneously, okay? And he thought, oh, that's interesting. So it depends on the velocity. And then he thought, oh, what if I increase the diameter of the pipe? And then he used a bigger pipe, bigger pipe, bigger pipe. And then he saw all of a sudden, okay, now again, it bursts like this. And it's also, the faster transition, with a larger diameter. Then he used different fluids with different viscosity, here kinematic viscosity, and he found it's inversely proportional to the viscosity, okay? And then, of course, the other way to do this would be take the incompressible Navier-Stokes equations, make them non-dimensional, and then all of a sudden you see there's a non-dimensional group popping up in front of the viscous term, which then we call the Reynolds number. Okay, so this is how a turbulent flow then looks like. I have this turbulent flow here in this turbulent pipe. I do a measurement of the velocity at a given point. And the flow is kind of stationary in the mean, but you have these local turbulent fluctuations. And so I do a measurement, and this is a kind of a velocity signal I measure. And you see, it's kind of, you have a mean velocity, a velocity around which this fluctuates, and then you have these fluctuations. And you could say, in a way, the mean is kind of here maybe a deterministic quantity. From this I know what the mean will be a lot later. And this is, by the way, an example where the mean is also time dependent. Can also happen, but so this is, but this, let's say, is how this looks like. Now, this we said already. One thing we didn't say, turbulence is always 3D. Turns out, we're not going to talk about this much more, but it turns out if you have a two-dimensional flow, it cannot be turbulent. That is because of what's called vortex stretching. You have the mechanism for turbulent dynamics depends on the process where you have a vortex, it goes like this. A vortex is two-dimensional. And that vortex is being stretched. In fact, the transfer of energy from the large to the smaller scales happens through this vortex stretching. And if I have a vortex in 2D and I want to stretch it, I need the third dimension. I can't stretch it in these 2 dimensions. So turbulence always 3D. You know, that's why large eddy simulation, where we try to resolve some of the turbulence, they're always 3-dimensional simulations. You cannot do 2-dimensional simulation where you want to resolve, let's say, part of this, also direct numerical simulation. They're always 3D. Do you see anything else here? Vorticity is important. And of course, this transition happens at large Reynolds number then. Now, one important technique to analyze turbulent flows is the Reynolds decomposition. So really, you know, in engineering, sometimes we are not interested so much in the fluctuations. We're interested in the mean mixing rate, you know. I mean, the fluctuations happen on very short time scales. We are really interested in seeing, you know, in this engine, do we have enough space, do we have enough residence time for fuel and air to mix, for example. So we are often interested in mean quantities, which is why we introduce this Reynolds decomposition, where we say the local instantaneous velocity, we decompose it in a mean and a fluctuation. Okay, so how do we define the mean? There are different ways to do this. One would be just to take here what's called an ensemble average. I do many experiments at one point, and I just take the average of these individual experiments. I could do this in every point in this room, and I get a mean velocity in every point in this room. The other way to do this would be to take a time average, but that, of course, only works if the mean is independent of time, right? If the mean is a function of time, this doesn't work. People sometimes say, well, maybe then I do the averaging window, I don't make it, you know, so large. No, then you don't get the mean. I mean, for the mean, to really get the mean, the time averaging window has to be infinitely long, right? It has to go from now to infinite time. So when I think about this, I always think of the ensemble average for 2 reasons. I mean, first of all, I mean, it's a correct definition, it always works. And secondly, it's a sum, okay? It's not an integral. Most people like a sum, find a sum easier to think about than integrals, even though it's the same anyways. But, I mean, this makes it easier also, you know, to work with differential equations sometimes a little easier. Okay, so that's what we do. We do this Reynolds decomposition where we define the mean like this, and then the fluctuation is just the difference between the local instantaneous and the mean. So going back to this picture, at each point in time here, you see the mean is the straight line, and then the fluctuation is always the difference. So the fluctuation is positive sometimes, and sometimes it's negative. And of course, it's defined such that the average of the fluctuation is 0. It's very, I mean, using this definition, very easy to show that this will be 0. Okay, so here, this is what this says. The fluctuation is defined so that the average of the fluctuation is 0. And then here, of course, if you have, you know, one fluctuation times another fluctuation, and I average these, you know, they're not necessarily 0. And I mean, an easy example is if I take, you know, just so here, if I have a fluctuating, I mean, a velocity fluctuation, it goes like this. So this is u prime as function of time. Let's say this is 0. It here fluctuates around 0, and then so if I average this, it will be 0. But if I take u prime squared and average this, if I take the square of this, then, you know, it will be all positive, right? And if I average a positive function, then it's not 0. So you know, correlations of different fluctuating quantities, they are not 0. Okay, so in fact, we call this here, I mean, this is the example I just showed, this is something like the standard deviation, or as we call this here, the root mean square. So this is the fluctuation, squared mean root. So it should be called square mean root, but it's called root mean square. So, what's interesting then, if I write the Navier-Stokes equation, in our case, we have typically variable density flow. If we have variable density flow, then I start out here with the, let's say with the momentum equation. The first term is d rho u divided by dt. And then if I introduce the Reynolds decomposition here, then I get d by dt of rho mean plus rho prime, and then times u mean plus u prime. And you see here I get a term rho prime u prime, and ultimately, you know, when I take the average of this, I get a lot of these terms. I get a lot of correlations between density and something else. So that makes things very complicated. And so somebody came up with a smart idea to introduce a density-weighted average. And it's defined in a way that just that these correlations here don't appear. And that's shown here. That's called the Favre averaging. So that for us is typically relevant. So, so this is what I just wrote here. Exactly. So I get these correlations here. And so now I introduce a Favre averaging. I call this U tilde and U prime prime. You know, it's different from Reynolds averaging. And then, so I define this. So I get these correlations here. And I just want to define it, or these correlations, I want to define it so that these correlations here are 0. And so if I take rho u mean, it is rho times u plus u prime prime, which is rho u mean, u tilde, plus rho u prime mean. And I define it now so that this is 0. That's my definition of the mean. And then, you know, I can here solve this for u tilde is then rho u mean divided by rho mean. Okay, so that if I define my mean like this, then this will be 0, right? So that's then, here that's what we call then the Favre averaging. And it will lead to the fact that, you know, something like this. Now if I do the same thing here, I average this, it will just give me a rho mean times u tilde, okay? So I don't get these nasty correlations. Okay, so there's also then, so that's not the same as, you know, just an ensemble average. This is the density weighted average. Is not the same as this, but there is a, you know, a way to convert one into the other. It turns out the differences are usually not very much, and we write the equation, we solve the equation, we usually use here this Favre averaging. We don't need to worry about it typically very much. The only point where you need to worry about it is when you want to compare a simulation with an experiment, because the question then is, you know, did the experiment, you know, evaluate this mean or that mean? That's important to know. Okay, so then for non-constant density, Favre averaging leads to much simpler equations. Okay, then if we go back, look at turbulent flows, this just shows a few pictures here of direct numerical simulations. So what are direct numerical simulations? We write the Navier-Stokes equations, and we know they describe turbulence. They describe also all the randomness of turbulence, which for a long time was questioned by researchers before one was able to solve these. They said, you know, an equation, if you specify initial condition and you have an equation, it's deterministic. But of course now, you know, with chaos theory and so on, we know that's not true. You always have a disturbance inaccuracies. You cannot specify a state, you know, to absolute accuracy, and then even though you think you have exactly the same, it's very slightly different. These perturbations in a nonlinear system, they can grow up to the point where they are of leading order, right? And so this will change then the local fluctuations. It will not change the mean, but it will change the local fluctuations. So that's what we say, the local fluctuations cannot be predicted. So these are a few examples here for relevant cases. A round jet is a relevant case. A flow around an airfoil, for example, flow in a combustor. And you see here we are typically concerned with flows that are related to combustion. Now, there are two different ways to produce turbulence. Turbulence comes from gradient, from shear. You have shear and you have viscosity, and that creates vorticity, okay? And the vorticity then makes these maybe large eddies, and they make smaller eddies and so on. So there are two ways to produce shear. One is to have a free shear flow. I just have like a jet, I just, shoot, material into another material, like here in this jet. And the second one, to have a gradient or shear, is to have a flow along a wall. Because a wall always, has a no-slip condition. The flow at the wall, the velocity at the wall is always zero. And if I flow past the wall, I get shear. I get a boundary layer and I get shear. So we distinguish between free shear flows and wall-bounded flows, okay, when we talk about turbulence. And because combustion, usually we try to have it away from walls, the generation of turbulence comes typically from these free shear flows. So here we are more concerned with free shear flows than with boundary layers. So we're not going to talk about boundary layers here. Now, one thing that's interesting is we said earlier you have these turbulent eddies. And if you look at a picture like this, you don't see an eddy. I don't see anything that's really spinning. But what you do see, if you look at it, you kind of see coherent regions, I would call it. I would call this here, this yellow spot, I call this a coherent region. This yellow spot is a coherent region. This dark spot is a coherent region. And then again, if I look inside this coherent region, here, if I look down at the larger scale, again, here I get a spot where I would say this seems coherent, here a darker one, here a darker one, and so on. So you get these, and if you would look at the motion, these are regions also, they kind of move together, okay? They don't go like this, but they kind of move in a coherent way. But then inside, these coherent structures or motions, you get smaller coherent regions, or here actually you see an eddy really, or, even smaller coherent regions, so you get a lot of different scales. So we have sometimes in these simulations, so here this is a simulation of a shear layer, you have a flow that goes to the right on top, a flow that goes to the left on the bottom, and this here really just shows here scale dissipation rate. This is really the local mixing rate. This is where, we have strong turbulence, and then, you see that you get a strong change if I go from the top here to the bottom, if I look at the cross-section. But if I look at from the top at this thing, that's how the simulation is done. It's homogeneous in this direction. It's all the same in this direction. But you see there are changes, so we say it's statistically homogeneous. The average values, they are all independent of position in this direction. But of course, locally, or at one instant in time is different. So from that, then we define, that's very often used in turbulence theory, and also when we do simulation, these DNS simulations. Oh, I didn't say what DNS simulation is, sorry. I got sidetracked. So what is DNS simulation? We know how to write the Navier-Stokes equations. We know they describe the turbulence. So we can actually solve the Navier-Stokes equations without any assumptions, okay? And that gives us simulation results like this, if the Reynolds number is large enough. The problem is, and I'm not sure if this is mentioned here somewhere, how large these simulations are. So this simulation here is a very simple flow. It's let's say a small box, a cubic centimeter of turbulence. It's a relatively high Reynolds number, but the simulation is done on 2,000 times 2,000, 3 dimensions, on 2,000 cube points, okay? So that's like 10 billion points. And then, imagine we want to do combustion. So 10 billion points, we have 5 degrees of freedom. We have the pressure and 4 degrees of freedom, the pressure, and 3 velocities, and let's say the density in our case. So let's say it's 5. So that's, what did I say, 8 billion times 5 is 40 billion degrees of freedom. And then if we do a multi-step chemistry, maybe you have 40 species or so, then you are more at 50 times 8, which is 400 billion degrees of freedom. Okay? So these simulations, even if you look at very small box, they get very, very large. So we use these not to compute a full combustor. We use these to compute a small little thing to understand what's going on. Okay? Right, and so when we do these simulations, it's good to have simple systems. So sometimes we define these simpler configurations. One is called homogeneous turbulence. Homogeneous turbulence means the turbulence statistics are invariant under translation in space, okay? Which means if I measure turbulence statistics here, you know, I get certain, let's say, velocity fluctuation in this direction, and maybe much smaller velocity fluctuation in this direction, let's say. But I measure these, and then I go to some other place in space, I measure velocity fluctuation in this direction, I get the same values as over there. It doesn't mean they're the same in all directions, it just means they're same everywhere in space. That's kind of like, what you see here, this here, seemingly, no matter where you are, it always seems to be the same, or here, the local velocities are not the same, but the statistics here will be the same everywhere in space. And it will be different in this direction or in this direction, but they're independent of where I sit in this plane, let's say. Okay, so that's what we call homogeneous turbulence. And then, the nice thing about homogeneous turbulence, what's interesting, is that, you have this homogeneous, it's the same everywhere in space. Gives you a lot of easy statistics. You can average, the statistics over the whole space. At the same time, it allows to have a velocity gradient, as long as the velocity gradient is the same everywhere, So you can have a constant shear, and constant shear means you produce turbulence. So homogeneous turbulence is nice because it produces turbulence. And then the other simplification that we often make, which also in a way is very technically relevant, and I'll tell you later or maybe tomorrow why this is what's called here isotropic turbulence. Isotropic turbulence means the statistics are invariant under translation in space, but also invariant under rotation of the coordinate system, which means I measure now velocity statistics in this direction, I get a certain value, and then I turn around, or I close my eyes, you turn me around, and then I open my eyes, I'm in a different direction. Now I measure velocity statistics in this direction, and I get exactly the same. It's in all directions, it's the same, okay? There's no directional dependence, which means the mean velocity needs to be 0, right? If the mean velocity goes this way, it's different from this way. So the mean velocity is 0, and then you get fluctuation in all directions. Because the mean velocity has to be 0 everywhere, there's no turbulence production. So this leads then to decaying turbulence. You start out with turbulence, but the turbulence decays away. Okay, so let's look at the equations. Mean flow equations, that's interesting actually. So here we do this just for incompressible flows because it's easier to understand. But of course, if you want to do this for combustion, you have to do variable density equations, and also you need to use then the Favre filtering or averaging and not the Reynolds filtering. So this is the continuity equation, and this is the momentum equation. And one thing that you probably know is that here in this convection term, so it's time-dependent term, convection term, this pressure term, and the viscous term. And, again, if we think of what do these terms mean, du dt is clear what it means. It's the time rate of change of the velocity at one point. This convection term is basically, so these equations are written for a fixed point in space, right? And so, if I sit here and somebody walks by, I just sit here and look in this direction. Somebody walks by, I first see it getting dark, and then I see it getting light again. And that's what this convection term does. It just pushes the fluid, It just pushes the fluid through a certain point, which means if I have here a velocity hump, okay, and I sit here, and then the convection pushes this by, then I see the velocity go up and then go down, okay? So that's exactly what this does. And the funny thing is, I mean, this thing wants to push the velocity by, but it does it with the velocity. And so, you know, if I have, let's say I have a velocity gradient that looks like this. So here's u as function of x, and the velocity looks like this. It's low here, and it's high here. So this is positive velocity. It would push stuff in this direction, right? But it would push this point here not as fast as this point, right? So a little later, this profile looks like this, right? Because the higher velocity moves faster. A little later, it looks like, it looks like this, but this gradient will get larger and larger, or, you know, that's a nonlinear effect. How do you see this? Look at the equation. This term is nonlinear. U times u. That's the thing. All the rest of the equation is linear. So if you think of turbulence, turbulence is something chaotic and blah, blah, which means there must be some nonlinearity. And that's, you know, you look at the equation, that's the nonlinearity. So this is the term that causes all the interesting stuff in turbulence. Without this term, there's no turbulence. This is also the term that causes shocks, you know. I mean, things like this. Anything complex always comes from this term. So this is the, and then the viscosity, of course, tries to do the opposite. You have a profile that looks like this. Okay? Viscosity says a little later it looks like this. Okay? So this term tries to make the gradient really large, and the viscosity says, no, I want to make the gradient really small. Okay? It distributes stuff in space. So this is the Joker, this is Batman. You know, this always tries to make chaos. And this here always tries to, no chaos, you know, we have to take it easy. So, and then here the pressure term is just acceleration, right? I mean, if I want to move something from here to there, if I want to move the desk, I need to push on one side, okay? And not push on the other side. You know, then I move the desk. Actually, it's difficult to move this, but if I have a higher pressure here and a lower pressure there, then stuff moves. So if I want to move fluid, I need to have a pressure gradient, right? A pressure gradient will accelerate the flow. We call this a favorable pressure gradient will accelerate the flow. An adverse pressure gradient will decelerate the flow. That's all the pressure does, right? It's funny because, I mean, push and pressure in German is the same word. Isn't that interesting? I mean, that's what I just said, you know. I think in German, it's much easier to understand the effect of pressure because, you know, I mean, the German words, I pressure you know, it's the same word. Anyways. Okay, so that's what these terms do. And what was I trying to say? I mean, so all the interesting stuff needs to come from this term. That's it. Oh, no, really what I wanted to show you is this. I mean, here we write this sometimes in what we call the non-conservative form. How do we write now? We say ui times duj by dxi, okay? But that is the same thing as, or I could say dui uj by dxi is equal to this plus uj times dui by dxi, right? And this here is 0 by continuity, right? First equation up there, this second term is 0. So this means this ui, I can always push it inside or out here, right? I mean, I can just you know, this is the same as this. So push it inside out. We use this sometimes, so that's why I'm just saying this. So, so let's introduce this Reynolds decomposition into these equations. We start out with the continuity equation. So we say dui by dxi is equal to dui mean plus by, let's say, by dxi plus dui prime by dxi. Right, that's just introducing the Reynolds decomposition, and now we average the whole thing. Turns out the averaging operator, it commutes, I mean, it's a sum, okay? So it commutes with the differentiation. So I can write it as dui, sorry, this is, no, this is right. Bar divided by dxi plus dui prime bar by dxi. And this one here, the second one, was 0 by definition, right? So this here is 0 by definition, and the first one is ui bar. But if I average a mean quantity, it's still a mean quantity, right? So this here, you know, I can take the second bar away. And then you see the mean continuity equation is just this. And if I subtract this from the original equation, I find this is also true. So the continuity equation says in an incompressible flow is divergence-free. That's what this says. And the mean velocity field is also divergence-free, and the fluctuation field is also divergence-free. So, you know, that's what it is. And what's interesting is that the equation for the mean looks exactly the same as the equation for the instantaneous quantity, right? And why is that? That is because it was a linear equation. For a linear equation, I can always, you know, split these two up, and, you know, I always get the same. So if we look at the momentum equation, we said all of the terms are linear, and you will get exactly the same. This term here will just end up having the bar here, I mean, uj bar. This will be p bar, and this will be u bar again. All the linear terms will do exactly the same. But luckily, we have a nonlinear term also. Otherwise, we would be bored by now. So we look at the nonlinear term, okay? So nonlinear term, I said I can move the ui inside by continuity. So I get this. And now we introduce the Reynolds decomposition for both of these. So I get ui bar plus u bar plus u prime. And I get 4 terms from this. Here is u bar term, and then one u prime, and then u prime. And then I take the average of this, okay? It's always the same when you derive these equations. First introduce the Reynolds decomposition, then do the averaging. And you see the first one is an average already, that doesn't change. This one here is then u prime average. This is 0 by definition. This one here also 0 by definition. If I average this, we said earlier this is non-zero. Okay, so this term here remains. And it turns out, so when I then put that back in the equation, this is how the equation looks like. As I said, the time-dependent term doesn't change really. It's just written for the mean. Then we have this comes from this term here. It's just also this convection term written for the mean quantities, pressure for the mean pressure. This was the viscous term, and then now this is the new term, okay? And the question is this term important or not? Can we neglect it or not? What do you think? Who thinks we can neglect it? Who thinks we cannot neglect it? Okay, very good. Thank you very much. Of course, if we could neglect it, then turbulence had no effect on the right? Because then it would be exactly the same equation. Same equation, same boundary conditions, you would get exactly the same solution. But, so this term here, if we say, I didn't say this, but you can show that a turbulent flow, I mean, you need a certain Reynolds number for the flow to become turbulent. And that minimum Reynolds number, at that minimum Reynolds number, you can show that the mixing is 100 times faster than for a laminar flow, okay? So even the mildest turbulent flow mixes 100 times faster. So this 100 times faster mixing, it all comes just from this term. So that's what we call the Reynolds stress tensor. It has, it's a tensor, UJ, and it has nine individual terms. It's symmetric, so it has only 6 independent terms. You know, the upper right are the same as the lower left, but it has 6 independent terms. And what's interesting is we don't know what these are, you know. I mean, we have this here used to be, or if you look at this here was our system of equations. We have 4 equations, 1, and these are 3 equations here, right? You know, one for U1, U2, and U3. So we have 4 equations. We have 3 velocity components and the pressure unknown. This was incompressible, so the density is given. So we have 4 equations for unknowns. Here, now, this was 1 equation, and then here we have 3 more equations, but now we have the mean pressure, 3 mean velocity components, and we said 6 components of the Reynolds stress tensor. So we have 10 unknowns, but we have only 4 equations, okay? So that's what we call the, here the closure problem in turbulence theory. These equations, we cannot solve them. We need more equations. You know, we need 10 equations if we have 10 unknowns. Okay, so this is the quantity when we talk about modeling. This is the quantity we need to model. So I think we are out of time. Maybe we stop here. So the first idea would be to maybe we just derive an equation for this. These are the so-called Reynolds equation we see that makes it even worse. These will have even more terms that we don't know. So let's do this tomorrow. Have a good evening. See you tomorrow.